All right, question 2 on the Unit 3 FRQ review. We are given the equation for a curve and we are asked to find dy dx. So just a quick reminder that when I write d dx, that is an operator. That is telling us to take the derivative with respect to x, whereas dy dx is the same as y prime. So when I take the derivative of y, then with respect to x, that is what becomes our dy dx. And again, we said that in y prime, those are interchangeable ways of writing the same thing. All right, so I know this is an implicit differentiation problem because I cannot isolate y. I have a cubic y term, so I won't be able to isolate y. So I'm just going to start by taking the derivative of the left and right hand side of the equation with respect to x. So using the power rule, when I get to 5xy, I'm now using the product rule because 5x and y are both, x and y are both different variables, so I have to use the product rule. Because this is after addition, here parentheses do not matter, but if I had a subtraction, like if I was subtracting 5xy, then I need parentheses because that would apply to both terms generated by the product rule. All right, so when I take the derivative of 5x, I get 5 and I multiply that with y. And then when I take the derivative of y, I get y prime or dy dx and I multiply that with 5x. Oops, not if I don't write it correctly. And again, you can write y prime here if you want. And then lastly, when I get to my y cubed term, that becomes 3y squared from just using the power rule. But again, I've got to use the chain rule because it wasn't an x cubed, it was a y cubed. So I have to multiply by the derivative of y with respect to x. On the right-hand side of the equation, since I have a constant, don't forget to just make that 0. All right, so since my implicit derivative has yielded two terms that have a dy dx or a y prime, I need to keep those two terms on one side of my equation, and then I want to send any other terms that don't have dy dx to the other side. So I'm going to just add 16x to both sides, and I'm showing this step where I'm doing this on both sides because this is, a help video, but what I'm writing in orange, you don't have to write. You do need to show your work on a problem like this, though. All right, so on the left-hand side, those terms have canceled out. So now you can show these steps if you want, though. So now the left-hand side of my equation is 5x times dy dx, and the right-hand side is 3y squared dy dx, or y prime. But over here now, I have that equal to 16x minus 5y. All right, so now my two terms that have a dy dx in them, I'm going to factor out dy dx. And in this case, it is the only common factor of those two terms, well, besides the number 1. But if it were not the greatest common factor, I would still only pull out a dy dx in this step, just for ease of isolating dy dx. That's our whole goal. All right, in our very last step, well, I hope, hope it's our last step, I'm going to divide, because the left-hand side of my equation is two factors, right? I have dy dx times some junk in parentheses. That junk is 5x plus 3y squared. I'm going to divide both sides by the factor of 5x plus 3y squared, and that will isolate dy dx. So my final answer is dy dx equals 16x minus 5y over 5x plus 3y squared. And as I told you in class that on a AP exam question, they usually actually give you the derivative and say, show that dy dx equals this. You still have to do all that work. The good thing is you actually just have the answer. I also just want to point out that there is nothing that we could simplify in our derivative there. I cannot divide out 5s. I can't divide y's. I can't divide x's. That is because both the numerator and the denominator are two separate terms, and neither expression on top or bottom has any GCF that I could factor out, so we leave it. All right, in part B, write an equation for the line tangent to the curve at the point 4, -1, 4, -1. So if I think about that, that is the point of tangency. So that means that that point is on both the curve and it's a point that I can plug in to my derivative. So the order in which you do these two things doesn't necessarily matter, but actually, never mind. I think I was about to complicate something in my head. Never mind. There's only like one first thing we need to do here. So again, when we write our equation for the tangent line, we can use point slope form. And here we are already given the point. I think I was trying to make this harder in my head than it was needing to be. So if I think about it, if I'm using point slope form, the only other thing I need to write the equation for a line would be the slope. And I know that the slope is going to be my derivative evaluated at this point 4, -1. So to show that I am evaluating the derivative, it's really important that we show what we are doing to earn credit for what we are doing. I'm going to write dy dx, and then we make this like long vertical bar here. And then in parentheses, kind of under that bar, when I write 4, -1, the way we read this, and this isn't just an AP thing, you'll see this in all sorts of college text. This shows that I'm going to evaluate dy dx at 4, -1, and here's what it's equal to. All right, so I'm going to plug in. So my dy dx is 16x minus 5y over 5x plus 3y squared. Again, I'm going back to part A for that. So I'm going to substitute 4 for x. I'm going to substitute -1 for y. And the most common mistake that I make, that I see other students make too, is sometimes we accidentally switch the x and the y. So just go slowly if you can. All right, so now if I simplify this, I've got to do a little math. And again, I know it's tempting if we're doing this work at home to use a calculator, but I would encourage you not to, since you will not be using a calculator on a problem like this. So if I'm multiplying 16 times 4, I might go old school. I might use the distributive property. I know 4 times 6 is 24. I know 4 times 1 is 40. Nope, is 4. Sorry, I was thinking of 40 because I put a 0 there. And I could just add those together. Or you could just distribute 4 over 10 plus 6 and get your answer that way. So we get what, 64? I bet a lot of you guys could just do that in your head, but it's been a long day, so I'm tired. All right, so 64. When I clean this up, I'm going to get 5 times -1, but I'm subtracting that, so that will become plus 5 over, 20 plus 3, since -1 squared is a positive 1. All right, so we end up getting 69 over 23. And that is not something that we could simplify since, oh wait, yes it is. I was about to say 23 is prime, which is true, but 69 is 23 times 3, isn't it? All right, so that just becomes the whole number 3. All right, we've shown our work for finding the slope. We were given the point, so our final step is to just actually write the equation for the tangent line. And again, I would use point slope form. So we could do like y minus y1 equals m times x minus x1. Or sometimes we add that y1 constant to the other side. Whichever one is more comfortable for you. I would discourage you from trying to distribute. I mean, you can, but I just wouldn't do any more math than I need to so we don't accidentally make a mistake. So I'm going to use the first form just because I think that's what I've done in all the other videos for this unit. So y minus y1, well, this is my x1 comma y1, because remember that's the point in point slope form. So that's a -1. That equals 3 times x minus 4. And you could leave it that way. That's fine. It's okay that it says y minus -1, but I'm sure you know that is also y plus 1. Now, if it were me, I wouldn't go any further because this answer is correct and I don't want to accidentally make a mistake when I distribute the 3 in combined like terms. All right, in 2C, we are told that there is a number k. So when that says there is a number k, that means k is an unknown constant, not a variable, so that the point 4.2 comma k is on the curve. Using the tangent line that we found in part B, we want to approximate the value of k. So remember, like if I have a curve, just drawing some kind of curve there. If I have a tangent line on my curve, when I'm close to the point of tangency, I could get a good approximation. So like when I plug in 4.2 to my tangent line, I'm going to get something near the point of tangency, but it will be a value on the tangent line itself, not the curve. So that's what we need to do here. So remember, this is an x value, this is a y value. So I'm going to take my equation from part B. So like y plus 1 equals 3 times the difference, x minus 4. And I'm going to plug 4.2 in for x. So let's see. Y plus 1 equals 3 times 4.2 minus 4. And 4.2 minus 4 is just 0.2. Whoops. There's a decimal there. All right, and then that becomes 0.6 when we multiply. And then lastly, I could subtract that 1 from both sides. So when I do that, I get, let's see, 0.6 minus 1 would be a negative 0.4. All right, so going back to the question said there's a number k, so that the point 4.2k is on the curve. We're asked to approximate the value of k. I would take this one step home with saying like k is approximately. You could either write it in that line or you could just write it out here. But our answer should be in terms of k. All right, part D, write an equation that can be solved to find the actual value of k so that the point 4.2 comma k is on the curve. So I want to point out, we got to read these carefully. We are not asked to solve the equation, and that would be extremely difficult, perhaps impossible. I haven't even tried without using a calculator. So again, if I want this point to be on the curve, well, remember we have our equation for the curve already. 4.2 is an x value, k is a y value. So I just go up to my curve, which I have to scroll up because I forgot what it was. So let's see, negative 8x squared plus 5xy plus y cubed equals negative 149. I can see how this question might feel confusing, but it's actually pretty easy. I'm just going to take my curve. I'm going to plug 4.2 in for x, substitute k for y. So negative 8 times 4.2 squared plus 5 times 4.2 times k, because that was 5xy, plus k cubed, because that was a y cubed, equals negative 149. That is all we have to do there. We do not have to try to solve that for k. We do not have to isolate k. We have written an equation that could be solved. We're just not going to solve it to find the actual value of k.